In this lesson, we're going to go back and just recap the electrostatic field versus the induced field, so that if you have any type of multiple choice conceptual type question comparing the two, you will hopefully be able to answer those questions based on the analysis considerations on this page. Now, the total electric field, right, that we have here, the total electric field in any problem, in general, can come both from a battery in the problem, so giving us some electrostatic field and force component, and if there is changing magnetic flux, we can also get an induced voltage and an induced electric field effect. Now, conceptually, the differences between the two are listed here for you, and I'm going to start from the bottom, kind of go to the bottom line here. The bottom line is that the induced electric field is non-conservative, and the electrostatic electric field is conservative. For the electrostatic field, voltage gives meaning to potential energy, namely delta U equals Q delta V, right? And voltage equals ed, integral E dot dx. All of the mathematics works, right? The integral of the electrostatic field around a closed path is 0. E begins on positive and ends on negative. Here, for the induced electric field, we cannot say delta U equals anything. Nothing. So this has no meaning. So potential energy, the induced voltage, gives no meaning to the potential energy because the induced electric field is not conservative. The integral around the closed path does not equal 0. It equals negative d flux dt. So our relationship between voltage and the induced electric field is given by this equation, but it is not conservative. Delta U and potential energy has no meaning. We have no starting and ending point, and we only have the induced electric field while the magnetic flux is changing. Now, how do we problem solve if we have changing magnetic flux and a battery? And then we're going to look at an example that'll just deal with the changing magnetic flux because we know how to handle batteries in problems. But let's just talk about a circuit. So we're going to look at a simple circuit here where we have one battery, a resistor, and that's it. So that's the only elements of the circuit, and it's a closed loop. It comes back to where it starts. And what we see is that, for the sake of this discussion, if there is an external B field coming out of the paper, and if it is increasing in strength, that we would have the changing magnetic flux in the square area that the circuit presents in the plane of the page. Lenz's law kicks in, so we have an induced voltage being generated, making the induced current, producing B induced into the paper, right, to fight the effect that's causing it. We have the external B field coming out of the paper and increasing. So in terms of problem solving, if we were told, for example, that this is a, I don't know, let's make it a 2-volt battery. And if we calculated that while the flux was changing, our induced EMF was 3 volts, then we would treat it like a regular battery in the problem and have the total voltage being 3 volts plus 2 volts, 5 volts when we did our single loop Kirchhoff loop. The types of problems that you're going to encounter to problem solve will be similar to this, and I have an example on the next page to walk through with you to show you how to analyze putting in these induced voltage. I'm going to use batteries in quotes to help you problem solve. So let's look at that. So here we have a circuit with no batteries in it. So these are going to be the induced EMF ones. This blue one here and this red one over here, we're going to see are going to be induced voltages that enter into the problem in a moment. So let's hold off on that. What we are being told, what you have in your notes without the annotations, is just these changing B field regions. So we have two B field regions. One where the B field is going into the paper. So region 1, the B field is going into the paper. In region 2, the B field is coming out of the paper. And we're told that both of these B fields are increasing at a constant rate of 100 Teslas per second. And we're asked to calculate the current in the circuit. So, well, let's see what the effect of the changing magnetic flux is. Well, we were given the areas of the circles because we're given the radius. We know area is going to be pi r squared. So we can calculate the flux in each of those areas 1 and 2 that we have here. So we have these flux calculations. It's the voltage is d flux dt. It's the B field that is changing, not the area, so it's dB dt, and we were told that the flux is changing at 100 Teslas per second. So we have values for E1 and E2 based on the numbers we were given to work with. The areas, pi r squareds, and the 100 Teslas per second. So that's where numerically my induced voltages came from. And now to finish problem solving the problem, as you can see here, we very quickly get to a couple Kirchhoff voltage loops, because what we are going to do is use Lenz's law to look at the problem and say for section 1, all right, the B field is going into the paper and increasing, and nature wants to stop that increase, so it makes I induced in this sense, right, to make B field come out of the paper. So I'm going to draw in my induced voltage and put the value in that I was given, and just put that battery in there, even though it doesn't really exist. I'm going to assign it that value and put it in there. And then I do the same thing for region 2, where we have the B field is now coming out of the paper and increasing. So the induced current is going to flow clockwise to make B induced into the paper to fight the increasing B field coming out of the paper. And I'm going to put a battery in there, right, and use it as a assigned value battery. And once that's done, now I'm just going to solve it as a Kirchhoff voltage loop problem that we've solved before. So I'm assigning I1 to battery 1, I2 to battery 2. I1 and I2 come together at this junction to make I3. I've used interior loops. I used counterclockwise loops, L1 and L2, to get my sum of the voltage sources equals sum of the voltage drops for L1 and L2, following our Kirchhoff voltage rules that we've always followed. So please make sure you understand, you go back and review your Kirchhoff voltage loop to understand why the values are the way they are. The loop comes out of the battery in the positive direction, the positive terminal. It's a positive. If the loop comes out of the battery in the negative direction, it's negative. So the loop comes out of the negative end here. It comes out of the positive end here. So that's why those are positive. And then I look at my current and my loop directions to get whether my IR drops are positive or negative. And I set up my 3x4 and I solve it. So please make sure you go back and review how to solve your Kirchhoff voltage loops. But this basic procedure is used in problem solving, and I wanted you to see how to add in these induced voltage, batteries in quotes, to do solutions, which, based on what we've done to this point, I think is very doable for you. So there you have it. We'll practice more and talk about it in class.